না না ফ্যান Okay, good afternoon everyone. So today right now I'm going to actually give a research seminar, so not lecture that we had for last 3 days or 2 days. So today I'm going to talk, this morning we talked a little bit about anaerobic digestion process, right? So we learned the fundamentals and like how to do some theoretical calculation for anaerobic digestion process. So in now I'm going to be mainly I would like to share some results that from my research. So today I'm going to talk about breaking bottlenecks for next generation anaerobic digestion. So basically what are the challenges in anaerobic digestion and how actually like different approach can actually help us to overcome those barriers, okay, and make sure that actually we can make the anaerobic digestion process more sustainable for resource recovery and circular economy. So I think you already know who I am. I am actually Associate Professor of Environmental Engineering at the University of Alberta. But before we jump into research, I want to give a little bit of background about my university and my research background. So all right. So University of Alberta, we are located in Edmonton, Alberta in Canada, and we are known as oil province in Canada. Actually, we have the third largest oil reserve, okay, in the world. And province of Alberta is actually kind of like we have University of Alberta, and there is actually another University of Calgary. So University of Alberta, we are in actually top 100 universities in the world in QS ranking, and we are top 5 universities. We are one of the top 5 universities in Canada. We have about 200 different undergraduate programs. We have 41,000 students from more than 150 countries across the world, and we have 5 different campuses. So my department, I am from Civil and Environmental Engineering and School of Mining and Petroleum Engineering. We have 10 different research areas, as you can see here: construction engineering, civil engineering, and environmental engineering and science. So for environmental engineering, we actually offer in undergraduate program, we offer a specialization in environmental engineering, and for grad program we have both masters and PhD we offer. For masters we have both course and thesis based, and we also offer both degree in environmental engineering and environmental science. So in addition to student with engineering background, we actually recruit a lot of students from science background as well, okay, because environmental engineering is quite multidisciplinary. So like not just the student, even our faculty members, we have very different background. For example, like I did my undergrad in chemical engineering. We have people from chemistry, we have people from biology, people from physics, okay. So lot of very diverse actually group. And our department, actually our strategic focus is we focus on 3 different areas: sustainable energy, climate change and environmental restoration, and resilient infrastructure. Those are our 3 strategic areas, okay, that we are actually trying to grow our research program and teaching program. And we have most of the time between 60 to 70 faculty members, okay. Sometimes we have retirement and then we recruit new people. And 60 to 70 faculty members, actually considering that we are one of the largest engineering department in North America, okay. And we have in our department 500 plus graduate student, okay, master's PhD, and we have about 1,000 undergraduate students in our department. So my research, I focus on bioenergy resource recovery and biosensing technologies for waste and wastewater industries. And my research group, I combine environmental biotechnology. So we kind of engineer microbes, and that is actually combined with bioelectrochemistry. So electrochemistry combined with microbial metabolism. And at the same time, we also focus on different types of physicochemical processes, because we cannot achieve everything with just using microbes, right? So sometimes we may need help from different physicochemical processes. So some of my research focus these days, we focus on anaerobic digestion and fermentation, focusing on different types of value-added product, including methane, hydrogen. We also focus on different types of like value-added chemicals. My another focus area is microbial electrochemical technologies. We kind of look into different application, how we can actually combine this technology with anaerobic digestion process, how we can actually treat wastewater. We also actually focus on how we can actually use microbial electrochemical technology as a biosensor, okay, for monitoring environmental contaminants. And as we are in the oil province of Canada, okay, so like you have to have some research on oil sands sector. So I also work with one of the oil sand companies, Imperial Oil, and we are actually trying to develop some biosensor for monitoring some toxic contaminants in oil sand process water. And at the same time, I also collaborate with some of my colleagues on developing different advanced remediation technique for oil sand process water. So I have my research lab. We have about 2,500 square feet of research lab that is actually equipped with different, like bioreactor facilities. So my research lab, we have bioreactor facilities starting from, like a milliliter scale to up to 150 liter. So lab pilot, okay. And we have different analytical equipment as well, and we have also pre-treatment equipment, like this is per hydrothermal reactor, ultrasonic generator, incubator, and you can see a lot of different bioreactors. This area is for microbial electrochemical technology studies. So we have multiple potentiostat. I think in total we have about 25 channels that we can run. And yeah, so we have and in addition to my lab space, actually we also have some shared space in our lab, like for molecular biology work, we actually have a shared space, and some other like additional space that is shared. So even sometimes if we are run out of our space, we can go to the shared space and run our experiment. So, and currently I have 4 postdoctoral fellows, 8 graduate students, 6 PhD, 2 masters, and 1 undergraduate student. And over last 8 years, we actually worked with our research. Actually has been funded by different government agencies like ANSWER, Canada Research Chair, Canada Foundation for Innovation, Alberta government. I also actually worked with many different industries like Imperial Oil, AppCore, actually one of the utility companies that also actually run their business in US as well. City of Edmonton, our municipality, Veolia, actually it's a French company. And we also actually work with some consulting companies as well in area of water and wastewater. Okay, so that's I think enough of bragging about my university and my research program. So let's jump into now the topic for today. breaking barriers for next generation anaerobic digestion. So we already know that anaerobic digestion process, it's a multi-step biochemical process, okay, where we can actually degrade some of the complex organics that we have in our waste and wastewater, and we can actually produce methane as a like renewable energy, okay, and at the same time we can get biofertilizer. But some of the common bottlenecks, okay, in anaerobic digestion process is actually it's a slow process kinetics, okay. So the the reaction or degradation process is not fast. So that means like you need a larger footprint of your reactor that can actually cost increase the like not necessarily just the capital investment. So payback period is also high, and that is actually one of the bottleneck that actually people are not interested to invest in anaerobic digestion process. And when we operate the system at high organic loading rate, we can have problem about process instability, and at the same time the quality of biogas, it's a major concern, because biogas you have sometimes 30 to 50% of carbon dioxide, and at the same time you have sulfide in your biogas, right? So if you want to upgrade biogas to renewable natural gas, okay, you have to get rid of those carbon dioxide and sulfide, right? And sometimes it could be quite expensive process. So my research will look into how we can actually overcome those barriers, and some of the approach that we have is microbial electrocatalysis. So we try to combine microbial metabolism with electrochemistry, and two topics that we have been working on is microbial electrochemical technologies, like combining microbial electrolysis with anaerobic digestion. We also work on microbial electrosynthesis. So how actually we can convert carbon dioxide in biogas to some value added product. At the same time, we also work on conductive additive, application of conductive additive, because it has been actually demonstrated that when we add conductive material, we can actually promote a different kind of syntropy. So if we have conductive material in our anaerobic digestion process, sometimes instead of exchanging metabolite, some bacteria and archaea, they can directly exchange electron, okay. So that can also boost the process. Under physicochemical process, we work with thermal hydrolysis, hydrothermal liquefaction process, microaeration, nanobubble water, which is kind of an emerging technique right now that we have been working on, chemical precipitation for nutrient recovery. That's actually another area we have been focusing on. So our main focus is process intensification. So how we can actually increase the capacity of existing digester using different advanced approach. We focus on circular economy, how we can actually get more value added product, okay, and how we can actually extract more resource using anaerobic digestion process. And at the same time, my research group, we also look into environmental risk, like two things that we are have been focusing on for last couple of years. We look into microplastic and nanoplastics and antibiotic resistance gene, because that actually like antibiotic resistance is kind of a global concern right now. And sometimes the residual from anaerobic digestion process, you have antibiotic resistant, right? So if we use them as a biofertilizer, that could be a concern, right? That can actually spread the antibiotic resistance. So for interest of time, in this talk, I'm going to be mainly focused on some of our research in microbial electrocatalysis, and I would like to share some results here. So first I would start with a process called microbial electrolysis cell assisted anaerobic digestion. So what is that? In this process, we combine microbial electrochemistry or integrate microbial electrochemistry within anaerobic digestion process. So basically we introduce electrode, anode and cathode, and we provide power supply. So what happened? So we can actually grow some electroactive bacteria on the anode surface, and they can degrade organics and transfer electron to the cathode surface, where actually it can be electron and proton can be combined together and produce hydrogen gas, okay. So now hydrogen can be actually utilized by methanogen, okay, and produce methane gas. And I'm not sure whether you remember that I was mentioning that acetoclastic methanogen, they are like slow growing bacteria, slow growing archaea, slow growing microbes. And acetoclastic methanogen, they are slow growing, but hydrogen trophic methanogen, they are relatively, they can grow faster than acetoclastic methanogen. So what happened? Those electroactive bacteria, when we grow them, they can use the acetate. Okay, so they can actually, and their growth rate is faster than methanogen, so they can kick out acetoclastic methanogen from the system. So you have more hydrogen trophic methanogenesis, so that's the process is much more faster than conventional anaerobic digestion process. So, but if you go, and there have been lot of studies, and if you go back to the literature, you are going to see almost 90, I would say 99% of the studies, they use continuous power supply in this kind of research. Okay, so we have been thinking whether we really need 24/7 power supply to actually run MACAD reactor or not. Okay, so we did some experiment, okay, couple of years ago, and we used actually glucose as a substrate. We had a single chamber MACAD reactor, okay, and we actually ran an experiment. So we had first as a control, we actually supplied, okay, power for 24 hours, okay, and then we turned off for 6 hours, and then actually gradually we turned off for 12 hours, okay. And as you can see here, for 24 hours on and 18 hours on condition, we got almost same performance. And when we actually turned off the power supply for 12 hours, actually performance decreased. So still that means we can, within 6 hours, we can actually turn off the power supply and we can get same performance. Then we did further study with municipal sludge, okay, and we did the same approach, 24 hours on, 18 hours on, and 12 hours on. But this time we found that actually, like, even if we turn off the power supply more, actually we can get better performance even. Okay, so that means MACAD reactor, we don't need to actually provide 24/7 power supply. Okay, so that means actually we can actually reduce significantly the operating cost. So what is the implication of this study? Because if you think about throughout the day, okay, our actually electricity usage is not the same, right? So at night actually we basically turn off the light, okay, so we don't need actually, and even industry or some manufacturing industry, they don't actually consume electricity, right? But electricity is something that we cannot actually store, and at night we have a lot of surplus electricity. So that means actually during peak hour we can actually turn off the power supply in our MACAD reactor, okay. So or sometimes we can use the surplus electricity actually to run MACAD reactor, and that can be a very sustainable approach for promoting this kind of approach in the field. So next study we tried 3D printed electrode, and the motivation behind this study was, like sometimes we believe that actually if we provide more surface area, okay, for especially in attached growth process or any biofilm process, when you provide more surface area, we believe that can actually help you to retain more biomass in your system, and that can give you better performance, okay. But what happen if you have a certain working volume of your reactor, so and you are trying to actually provide more surface area, so that means you are actually adding more material, right, and that is actually reducing your working volume for your reactor, right. So now we can actually provide more surface area with actually certain working volume using 3D printed electrode. So we can actually fabricate some sort of electrode material with complex geometry, okay, that can provide you more surface area without compromising the working volume of your reactor. And as you can see here, so I worked on this project with one of my colleague from another university, who is actually an expert in additive manufacturing. So he actually fabricated some 3D printed electrode using carbon black and PLA as conductive filaments, and as you can see here, we actually came up with 4 design, and you can see split P is kind of more complex geometry, right, and cubic is more simple one. and split P provided about 40,000 millimeter square surface area, and cubic was only 15,000, okay, or close to 16,000. But when you have complex geometry, yes, it can provide more surface area, but it also increase the electrical resistance, okay. And cubic we had the lowest resistance. And then we did an experiment with glucose as a model substrate, and we had a single chamber reactor, MACAD reactor, and we did the same thing, 24 hours on, 18 hours on, 12 hours on, and 6 hours on, okay, intermittent power supply. So as you can see here, so for 24 hours on, actually split P, which had more complex geometry and more surface area, gave us the best performance, and we are happy, okay. But as you can see here, as we kind of move towards intermittent power supply, okay, actually split P was not giving us best performance. Cubic was actually giving more, I would say, resilient performance, okay. So for example, for 6 hours, cubic was the best, okay. So we try to explore, okay, what was the reason, okay. And actually my collaborator, he also did some computational fluid dynamics modeling, okay. And what we found, actually with complex geometry, maximum turbulent kinetic energy, okay, for split P was higher. So even also the fluid velocity on the surface of electrode, okay, was higher for split P, okay, and it was actually lower for other electrode. So that means regardless of high surface area, okay, other properties gonna be very important, okay. So more complex geometry, more surface area not necessarily ensure that actually you can get best performance, okay. So we believe, actually based on the CFD data analysis, okay, so high turbulence along with actually fluctuating power supply, actually split P reactor or split P electrode cannot actually kind of disturb the microbial communities on the electrode surface. So our result kind of emphasize that the geometry of electrode would be something really critical if we want to go with 3D printed electrode, okay. But again, 3D printed electrode can provide you, it can actually help you to manipulate the the geometry of your electrode, okay. So more actually research is needed. We are actually working on that right now. So next topic I want to move to is microbial electrosynthesis for biogas upgrading, okay. So we know that actually in biogas we have carbon dioxide, methane, and some other impurities like sulfide, and actually upgrading that biogas to renewable natural gas like 95 or 97% methane is kind of quite challenging. It's a very expensive process, okay. So how microbial electrosynthesis can help? So microbial electrosynthesis, we have like any kind of electrochemical system, we have anode and cathode, and on the anode, instead of like microbes, we have abiotic anode where we have water electrolysis, okay. And on the cathode, if we actually provide our biogas to the cathode, what happen? On cathode, because we are transferring actually electron from anode to the cathode. So in cathode we can actually produce that electron can be combined with proton and can produce hydrogen gas, right. And then hydrogen trophic methanogen can actually use carbon dioxide. If you remember the mechanism, carbon dioxide and methane can be used by hydrogen trophic methanogen and can be converted to methane gas, right. So we did an experiment, okay. So we had a lab scale microbial electrosynthesis cell, okay, and we had a gas bag that where we actually had biogas, and then we recirculated that biogas in the cathode chamber where we had microbes, okay. So first we started with sodium bicarbonate as a carbon source, and then we moved to carbon dioxide rich gas, okay, because we wanted to kind of go step by step. So first sodium bicarbonate, then carbon dioxide rich biogas, 70% carbon dioxide and 30% nitrogen. Then we tried synthetic biogas which is about 60% methane and 40% carbon dioxide, but no other impurities like sulfide. Okay, and then we tried real biogas from one of our project on agricultural anaerobic digestion process. That is actually was operated with agricultural biomass, and in real biogas we had about 215 ppm of H2S. Okay, and we had 4 different reactors, as you can see here. Anode was same, platinized titanium, which is kind of like an optimum electrode material for water electrolysis. And but cathode material we tried 2 different electrode, carbon felt and stainless steel, and we also had 2 different types of membrane. Okay, because proton transport from anode to cathode is actually key thing here, right? Because you want to produce hydrogen on the cathode, and for hydrogen production you need proton, and a proton transport is also important to maintain charge neutrality in the system, right? So first we tried sodium bicarbonate, and as you can see here, MAC2 was the best. So what we have MAC2? MAC2 we had stainless steel cathode and Nephyon 117 membrane. Okay, so and MAC3 was kind of second best. Okay, and we did some actually energy estimation or energy assessment for the process, and the result was not very promising in terms of energy recovery. As you can see here, energy efficiency was kind of not that good, mostly negative. Okay, so basically we are going to run the electrosynthesis process, electrolysis here, we are actually providing power supply, right? So we are providing energy to convert carbon dioxide, okay, to additional methane gas using microbes, right? So that means to make this process more sustainable, we should focus on like either use of renewable energy or use of surplus electricity. Okay, but again, like we as a researcher, that should not be the we should not stop there. If we see something is not energy positive, we can try to find other option to make it sustainable. But again, so now in next step we move to carbon dioxide rich gas, which is 70% carbon dioxide and 30% nitrogen. And at that part it was quite interesting. What we found that actually MES1 and MES2, okay, could convert CO2 to methane gas, but MEC3 and MEC4 actually did not work. Okay, those 2 reactors failed, and the common feature between those 2 reactors were they were actually having Nephyon 212, okay, membrane. So maybe that membrane is not very good for proton transport. Okay, somehow it was working with bicarbonate, but it did not work for when we switched to carbon dioxide. Okay, but if I compare the performance of MES1 and MES2, we can see so green is carbon dioxide and red is methane. As you can see here, for MES1 it took about 7 days, more than 7 days, okay, to see first CO2 is converted to methane, but only from day 2 we actually started seeing methane in the head space from MES2. Okay, so if I compare MES1 and MES2, the difference was actually cathode electrode. So MES1 we are having carbon felt, and MES2 we are having stainless steel. Okay, so stainless steel typically it's known as better electrode for hydrogen evolution reaction. Okay, so which is not very surprising that actually stainless steel was giving us best performance. So then we did some further study with MES2. Okay, so MES2 we thought that would be the most optimum condition for us, and then we tried MES2 with synthetic biogas and real biogas. So as you can see here, from day 2 synthetic biogas we could see actually it's 100% methane. Okay, we could not detect any carbon dioxide there, and even real biogas the result was quite comparable. From day 3 it was almost 100% methane, But the surprising part was, actually we did not expect that we are going to see significant removal of H2S, okay, but we found actually from just after 1 day of operation, all sulfide was gone from headspace, okay. So we did microbial community analysis for the cathode, and one interesting part is we could see after running with real biogas, we see Thiobacillus, actually some sulfide oxidizing bacteria, okay, they are specifically known for sulfide oxidation, okay. So those microbes, actually their abundance significantly increased on the cathode biofilm, okay. And so they could have two different pathways. They could either actually oxidize sulfide to elemental sulfur or sulfate, okay. But when you have sulfate, you can have some sulfate reducing bacteria like Desulfuro vibrio. They can actually convert sulfate to again sulfate can be actually reduced back to sulfide, okay. So but what we found that these sulfate reducing bacteria, their abundance actually did not increase. So we believe that the major pathway was those sulfide oxidizing bacteria, they converted all the sulfide to elemental sulfur, okay. So that means MES can provide dual benefit of this in situ desulfurization, okay, and it can also help us to actually convert those carbon dioxide in our biogas to methane gas, additional methane gas. But at the same time, we should focus on system optimization and use of renewable energy to make this process more sustainable. So now I am jumping into another topic. So addition of conductive material in anaerobic digestion, that actually became very hot topic in our research community over last 10 years. So it has been demonstrated that when we add conductive material like activated carbon, biochar, carbon cloth, magnetite, carbon fiber or any other conductive composite material, that can actually boost the biogas production. And many mechanisms actually have been proposed for that, okay. So but the key mechanism was direct interspecies electron transfer. So what is direct interspecies electron transfer? So when actually we have conductive material, those microbes, they can form biofilm, okay, on the surface of those conductive material, and they, instead of producing some soluble metabolite or gaseous metabolite, they can directly dump the electron, okay. And on the other hand, methanogenic archaea, they can take that electron and they can utilize proton and carbon dioxide, and they can actually convert that. So carbon dioxide can be reduced to methane gas, okay. Sometimes if you use iron based magnetite, so they are actually iron based conductive material, it can actually react with your sulfide and actually it can precipitate as a ferrous sulfide, right. So that means you are going to have less H2S in your biogas. Sometimes some sulfate oxidizing bacteria, like we are just talking, those sulfate oxidizing bacteria, the sulfide oxidizing bacteria actually, they can oxidize sulfide and can convert to elemental sulfur. That process actually also release electron, right, and that electron can also be used by methanogen. Some of those conductive material like biochar, GAG, we know that they are very good adsorbent, okay. Sometimes they can absorb excess ammonia, okay, and because we know that high level of ammonia can be toxic for anaerobic microorganisms, okay. And at the same time, actually when you have microbes, they form biofilm, okay, on conductive material, so you can easily actually achieve biomass retention in your system, right. And there are going to be some interspecies distance also going to be reduced, so that can actually help microbes to actually share metabolites with each other, okay, and enhance the process. So first study I want to actually share with you, it's the application of biochar for anaerobic treatment of black water with septic tank. And I'm pretty sure that most of you are familiar with septic tank, right. This is actually common approach in some countries in South Asia, and it's also actually very popular, okay, in some remote communities in developed countries, okay, or some recreational site, okay, like park or camping site, they actually have like septic tank system, because it's very difficult to actually connect those communities with centralized wastewater treatment facilities. So now that actually work was done by a visiting student from IIT Kharagpur. Actually he worked with me before COVID, like for almost 1 year, okay. So at that time we did this study. We kind of wanted to do something that can be valuable for both Canada and India, and that actually topic came to our mind. So what we did, we used actually biosolid from, so basically from wastewater treatment plant we collected biosolid, and we did a pyrolysis process at different temperature and we produced biochar, okay. And then we did a simulated septic tank system operation, okay, and we using synthetic black water, and our biochar loading was 25 gram per liter at produced at different temperature, and then we ran the experiment, okay, and we increased the organic loading rate starting from 0.08 gram COD per liter per day up to 3 gram COD per liter per day. And as you can see here, when we increase the organic loading rate, at low organic loading rate, there was not much difference. Either you add biochar or not add biochar, okay. So control and biochar reactors were actually giving us almost same performance. But as you can see here, when we move to after day 50, when we move to 2 gram COD per liter per day, okay, you can see the control reactors started to fail, right? And as you can see here, effluent COD here. So with increasing organic loading rate, our influent COD concentration increased, but for high organic loading rate, so those are biochar reactor and this is the control reactor. So control reactor, like it's kind of like the performance significantly decreased. So that means the addition of biochar can actually help us, okay, to achieve high rate septic tank system. And what I mean by high rate septic tank system, okay. So you know that actually nowadays, okay, we have like a toilet flush, okay. Conventional toilet flush, for each flush we use 3 to 6 liter, okay, water, right? But now we have more high efficient flushing system, right? So for each flush right now we use 0.5 to 1 liter, right? So what would happen when you have like those high efficiency toilet? So then that means your black water that you produce, that's going to be even more concentrated, right? You are going to have high like nitrogen, okay, concentration, high organic loading rate, okay. So that means your regular septic tank system that you have in your home may not work with high efficiency toilet. So you may think, okay, I'm going to save water, okay, I'm going to move to high efficiency toilet, but your septic tank system may not work, okay. So biochar, addition of biochar actually can help you, in this, solving this problem. So that was actually very interesting study, okay. So then with this morning we talked about high solid anaerobic digestion process, and you are already familiar with this process that we have a digester tank and we have a percolate tank, right, and we recirculate those liquid inoculum between two tanks to actually provide some sort of mixing. So when we looked into literature, we noticed that most of the conductive additive studies for AD, they have been done with CSTR reactor, like wet type anaerobic digestion process, and not much studies on high solid anaerobic digestion, okay. And I think still if you go back to literature, you are going to see very limited studies, and majority of their publication in this area from actually my group, okay. So we try to see how we can actually apply conductive material in this kind of process, okay. And one of the major challenges here, you are actually working with very complex feedstock, right. So first study we did it with powdered activated carbon. So we added actually powdered activated carbon in the leachate tank, okay, and then we actually recirculated that liquid inoculum, okay. And what we found, we could actually increase the biogas production by 20%. But now when we try to actually do some preliminary cost estimation, okay, we found that actually cost of our powdered activated carbon addition is about $6 to $30 per ton of waste treatment. But we can get 20% more methane, okay? But when you compare the revenue, we can just per ton we can get maybe $5. So it's not a huge amount, okay? So that means if you want to apply this kind of approach, okay, you have to reutilize that conductive material. But now we realize, okay, if we use powdered material, we cannot actually recover powdered material from digested. So we have to have some other material, okay. So the next thing, and the interesting thing is there are tons of studies on this topic and nobody talk about like the process economics, either it's feasible or not, right. And but one thing, we published this paper in 2021 and we mentioned that in our paper. In the following year we noticed that there was a study published that they were saying that there have been a lot of studies on adding biochar in anaerobic digestion process and that is not economically profitable, okay. So we have to have some material that we can actually recover or use for long term. So our next approach was using carbon cloth. So instead of powder, we thought, okay, if we use a cloth, okay, and it's going to be easy to use, we can actually layer our solid waste, then put carbon cloth and then put another layer of solid waste, okay, and then see if it works or not. So we did a study, we used laboratory scale reactor. So those reactor actually like 15 liter and those percolate tanks are 2 liter, okay. So then next study we did it with conductive carbon cloth and we found almost same performance, about 20% increase, okay. And we could actually recover the carbon cloth after the process is done. So then we wanted to see whether we can do some pilot, okay, using the same concept. And we had 2 pilot reactors, those are actually mobile unit, okay. So we have digester tank about I think 114 liter or 115 liter and our percolate tank was 45 liters. So total was almost 10 times of what we had in lab scale, okay. And those are mobile units, so if needed we can actually take them to the site for some demonstration study. But the first study we actually did it within the lab and we did the same thing. We had solid waste and then we put a layer of carbon cloth, solid waste, layer of carbon cloth, okay. And then the performance was quite comparable. In lab study we got 20% increase, pilot we got 22% increase, okay. So that means a process can be scaled up, okay. And at the same time we found that actually some microbes, they are known to actually facilitate direct interspecies electron transfer. So those microbes actually were enriched in carbon cloth reactor. But another interesting thing we found, we actually in the digested, we
are not supplying any electricity, just carbon cloth.
Yeah, just carbon cloth, yes. So just conductive material, so no power supply or anything, okay. So and then in the digested, we try to actually look into different types of antibiotic resistant gene, as you can see here, tetracycline, sulfonamide, beta-lactam, okay, and some mobile genetic element, okay. And when we compare, as you can see here, so carbon cloth reactor actually if you see in different phases like suspended, attached and percolate, or on average the gene copies for different ARGs were much lower compared to the control reactor, okay. So I think one of the reason is when actually you have any type of conductive material, you basically microbes, they are kind of immobilized on the surface of those material. So when microbes, they don't have lot of movement, okay, they don't have like their, so antibiotic resistance gene typically microbe they exchange that by horizontal gene transfer, right. So that gene transfer process or horizontal gene transfer process is actually kind of reduced, okay. So that might be the reason why we see in the digested in terms of like antibiotic resistant, it was much better. That was actually coming from carbon cloth reactor. So we also did a study using granular activated carbon, okay, to see if conductive material like granular activated carbon can help us to reduce the oxidative stress that can be induced by some emerging contaminant like nanoplastic, because that like different waste stream, now we have wide variety of microplastic and nanoplastic, right? They are emerging contaminant, and it has been reported that when you have microplastic or nanoplastic in your feedstock, okay, that can actually negatively affect anaerobic digestion process. Okay, so so then we did a study using polystyrene nanoplastic. We considered nanoplastic because we know that nanoplastic is kind of more negative impact on anaerobic digestion microbiome. So we had 150 microgram per liter, and we used waste activated sludge from wastewater treatment plant, and we tried two different concentration of granular activated carbon, 5 and 15 gram per liter, and we did batch BMP test, and I think all of you are already familiar with what BMP test is. Okay, so as you can see here, if I just focus on control and polystyrene nanoplastic, so control, here is the control and here is the polystyrene nanoplastic. So in presence of polystyrene nanoplastic, biogas production significantly decreased. Okay, but when we added GAC at two different concentration, as you can see here, it could completely alleviate the negative impact of polystyrene nanoplastic, and even could increase the methane production, okay, compared to the control. And we did measure the reactive oxygen species concentration, okay, the changes in reactive oxygen species. Why we did that? Because one of the key mechanism, okay, of when you have nanoplastic or microplastic in anaerobic bioreactor, they produce different types of reactive oxygen species, and microbes actually they don't like that. Okay, so because that species can actually inhibit microbial activity. So what you can see here, so this is actually changes in ROS level compared to the control, and as you can see here, GAC 5 and 15 gram per liter compared to the control, we could actually reduce the reactive oxygen species level. But when you have polystyrene nanoplastic, actually it increased significantly compared to the control. ROS level increased by 29%. But when we added GAC at different concentration, it could actually help mitigate some of the ROS generation. So that possibly the reason when we add GAC, that could actually reduce the ROS generation level. And antibiotic resistant gene, we like compared to our other study using carbon cloth, we found actually almost same performance. When we have like GAC, we could actually reduce gene copies of different types of antibiotic resistant gene compared to the control. But if you see here, polystyrene nanoplastic, when they were there, actually compared to the control, the abundance increased significantly. And why is that? Because microplastic and nanoplastic, they have their own negative impact, but at the same time they can serve as a carrier for other contaminant. Okay, so they can serve as a carrier for antibiotic resistant gene transport. But when we added GAC and at different concentration, we could see it could reduce the ARG abundance. So we believe it's the same mechanism. Maybe because GAC is porous material, so possibly some of the antibiotic resistant gene that were actually trapped in the pores, or maybe microbes, they were immobilized and they did not have enough horizontal gene transfer. So yeah, that's kind of like the mechanism we thought could be kind of like underlying mechanism. So those nanoplastic possibly could be trapped in the pores, okay, and like some of those antibiotic or ARGs could be trapped, or maybe microbes, they are immobilized. So take home message, so along with actually improving biogas, so conductive material, it has lot of potential. So not necessarily just we see improvement in biogas, it can also help us to deal with some of the emerging contaminants like microplastics and nanoplastics and antibiotic resistant gene. Process can be scaled up. Okay, so as I was showing that actually conductive carbon cloth was giving almost same performance in lab and pilot scale. but we need to think about process economics, okay, at the same time. So not necessarily, we get good result means that it can be actually feasible for practical application, and much remain to be discovered in terms of fundamental and real life application. Like, some of the mechanism, I think we should do more fundamental studies. So I would like to thank my, research partner and funding agencies, and my students, okay, my amazing team members who actually generated those results, and thank you for your attention. Yeah, I think, I'm not sure whether we have some time for Q&A.
Yes, sure.
Yeah, so please feel free if you have any question.
So
Yes.
I have a question. You have explained the mechanism of how granular activated sludge is inhibiting the gene transfer or antibiotic resistance.
Granular activated carbon. Yeah.
So that you have explained, but you didn't explain about how reactive oxygen species, ROS or RAS you call it. So how that is actually the concentration is becoming less.
Okay, yeah, that's a very interesting question actually. So what we believe, actually we explained that in the paper, okay, maybe, and for interest of time I did not explain it at that time. So what we believe, so ROS is basically generated when you have interaction, okay, with microplastics and microbes, okay. So when microbes, they are under stress, more ROS is actually generated, okay. But when they are trapped, those microplastics, you have less interaction between microplastic and microbes, and which also actually lead to less amount of ROS generation.
So is that experimentally proved, or you just corroborated the mechanism from the literature?
We measured ROS, but again, yes, it was from the literature. Yeah.
It's like granular sludge is more resistant towards toxicity. And we believe that granular activated carbon instigate the granulation formation.
So when you have conductive material, obviously microbes, they would form more aggregate, right?
Yes.
So they are going to actually form aggregate on the surface.
So the granulation could also be one of the reason for.
Yeah, possibly. Yeah, when you have really aggregate, so it's more going to be like biofilm. So your upper layer, okay, might be affected.
Might be affected.
But maybe in the inner layer might be still they could be more resilient.
Yes, because it's almost similar. I mean, not similar, but for SBR reactor, we are trying to add GSE to see how it can impact the granulation, so that it can.
Okay.
And we see in couple of results that addition of GSE it's increase the or it make the faster granulation process.
But for granulation process, there are actually other approach is available. Like so it's kind of like you can also try calcium, magnesium. Actually, you can try for granulation. But obviously, like when we add GAC, we might see some improvement. Yeah.
So did you differentiate between the biofilm forming bacteria which are present in the consortia?
So it could be both.
Yeah.
It could be both. Some microbes, they are going to be in suspension still. Some microbes, they are going to form biofilm there. Okay. So we try to take a composite sample. So from different location.
Okay.
So for example, when you have activated carbon, sometimes it's very difficult to differentiate from biofilm. But when we did, let's say, carbon cloth, it was easy to actually collect sample from the surface of the carbon cloth, right? But when we have powdered activated carbon, it's hard to kind of sample this kind of biomass.
Right. So because the efficiency can again depend on them, because if biofilm forming bacteria are favoring the process, then in that case addition of GAC or a carbon cloth can enhance the process, because they are ultimately getting a surface to adhere and then they can grow more rapidly. And in the other case, if they are more related to suspended form, then in that case their access to the nutrient might be hindered in case they are attached to the surface. So that mass transfer limitation can also be studied, like in this.
Yeah, actually we did, yes, we also did a study, okay. So trying different material and different mixing intensity, and we found actually, like, that could be a problem. Even more mixing sometimes actually negatively affect.
Yeah.
So yeah, so you have to optimize. So it's not just straightforward, okay. You need a very holistic approach to actually optimize different parameters.
Right. And regarding the 3D electrodes.
3D printed electrode, yeah.
So did you test the material affinity towards the microbes, like?
So yes, we did. We did analysis of microbial communities, and communities was actually different for different electrode material.
Okay.
Although they are same material, just different geometry, okay, but microbial community was quite different, interestingly.
And then you talked about the turbulence kinetics,
Yeah.
turbulent kinetic energy. So again, the I think the construction of the reactor can contribute to controlling that turbulence.
So that means actually, like like the hydrodynamics of the reactor would be a critical factor as well.
Right.
So here our reactor was same, okay, only the geometry of the electrode was different.
Right.
And so when you have mixing, okay, because of the geometry, the fluid velocity on the surface of different electrode was actually different. And those fluid velocity also actually affect the biofilm formation, right? Like shear velocity can actually, some microbes they can actually attach easily, some microbes they are going to be washing out from the system, right? So so the community was quite different actually.
Did you also explore the generation of ROS in previous system, where you have said that iron is there, sulfate, sulfide reduction is happening?
Actually you mean for
In electrochemical system.
for this one?
Yeah, this one.
Oh, this is actually just the mechanism. No, we did not actually do it by ourselves. That was actually, this is actually from one of our review article that we published, okay. So that was the mechanism from our literature review. But iron, there have been lot of studies actually, like if you add iron, it can, we know that actually even back in I think 2010, even my master's work actually was focusing on desulfurization. Yeah. No questions, so that means you understood everything. Okay. Well, yeah, so if there are not any more questions, thank you again. Yeah, so for staying that long and listening to me. Yeah, so yeah, thanks. Thank you.
From I think 9:15.
Yeah, 9:15 is good.